I'm Saryu Fensin from Los Alamos National Lab. Thank you for inviting me today to talk about my work. I kind of want to give you an overview of Los Alamos National Lab and the avenues that we have for students and faculty visiting the lab and collaborating with us. And then I want to go through some of the key capabilities within my team and go through an example where we were trying to use additive manufacturing as a way of improving dynamic properties of materials. Okay, the first thing I kind of like to begin with is how I kind of got to where I am. When I give seminars, a lot of students always wonder, right? Hey, what was the path that you took, for example, to get to Los Alamos? So briefly, I got my undergraduate at Mount Holyoke College, which is a small So I was graduate. I had done all my coursework and I was about to graduate about 6 months earlier than expected. And I remember I was talking to my advisor at that time, and she asked me, hey, what are you going to do? You're graduating 6 months early. And I had applications into graduate school, but then I didn't have anything to do for 8 to 9 months. And I said, well, I'm going to go work at Wall Street or something because they need chemists and physics, right, to make money somehow. It's all differential equations and I can solve those. But she was actually very kind and she said, well, let me try to find you a more appropriate internship in an area that you have an expertise in. So she reached out to a colleague at Los Alamos National Lab to try to find me a postbac position, which is basically a 1 to 2 year position that Los Alamos has available for people with a bachelor's degree. So that if you don't want to go to graduate school right away or don't want to get a job right away, this is a way for you to come work at the lab, see what working at a national lab is like. So I kind of worked at the lab for 9 months before I decided to go to school at University of California, Davis to work with Mark Asta. The funny thing is, if you notice on my slide, my PhD is actually in material science and engineering. I had done my undergraduate in chemistry and physics. That happened because of my experience at Los Alamos. When I was working at Los Alamos, I was working with a lot of people who were working on materials for nuclear reactors, etc. And I found that area to be really interesting and very application-based. So I decided that I'll go do graduate school in material science and engineering. I really liked working at the lab as a postbac. So after I was done with my graduate degree, I actually got a postdoc offer from the lab and I decided to accept that because of the positive experience that I had there. The only thing is, though, my postdoc was in a very different area than my PhD. So a lot of the students, I think, that they go to graduate school and do research in an area and then they feel like PhD was in computational material science. And my postdoc was looking at dynamic behavior of materials using experiments. So I basically went completely, not completely away, but kind of away from what my PhD was in. And then finally, I became a staff member in 2013 in the quasi-static and dynamic behavior of materials team, where I've been working since. Okay, so I like to also give students these talks is to try to solve complex problems. Might know, but Los Alamos National Lab is one lab out of many that is part of the DOE complex. It was first established in 1943 as under the leadership of J. Oppenheimer and General Leslie Grove. This task was achieved in 27 months. A ton of employees, a lot of them of the country. Is my audio still breaking up, Krishna?
I think it's for the most part it's okay, but once in a while there is a short.
How about this? Why don't I call in also?
Okay, yeah, that'll be great.
Okay, give me a, yeah, because this way at least you guys will be able to hear me. So give me a second. I'm going to stop sharing because I have to go to my email too.
Yes.
Should I restart or this is good? Okay, so I was talking about Los Alamos National Lab. So during Manhattan Project, we had employees, thousands of employees working at Los Alamos. Many of them were Nobel Prize winners. The cool thing about that project was when Manhattan Project was established, the location of Los Alamos was secret. In fact, people who came to work at Los Alamos couldn't even tell their families where they were going. Their only address was a P.O. box in Santa Fe. And to come to Los Alamos, people needed a special pass. So I kind of showed the gate here on the right side of the slide where you had to show your pass to even get into the town. That obviously has changed quite a bit since the 1940s. And big changes were made at the lab, actually, right after Cold War ended. Before Cold War, the focus was on designing and testing nuclear weapons. And after the Cold War ended and underground testing kind of stopped, more of the focus changed to making sure that the nuclear weapon that we have work as expected if we ever have to use them. Part of that paradigm shift involved doing more quote unquote non-warlike research, focusing more on basic science, working on other problems that can have a larger impact on the world. So here are some of the divisions, for example, or groups at Los Alamos that focus on that type of research. So for example, we have a large program where we've been doing research on fuel cell technology. We do a lot of global climate modeling. And when COVID was going on, LANL, a whole division in LANL was also involved in looking for cures and also modeling the spread of the disease, et cetera. So how do we kind of achieve, so what is our mission right now, I should say, and how do we achieve that? So our Los Alamos general mission is to solve national security challenges through scientific excellence. Well, how do we do that? The way we do that is by working in complex areas, solving difficult problems, by basically recruiting people who are really smart to come work at the lab. And one way we recruit people to come to the lab is by having world-class facilities, experimental and computational facilities that people can use. So if you guys weren't familiar, we have some of the world's largest supercomputers at LANL that we use to solve some of these science problems that I'm going to talk about later. Okay, so if you're a student or undergrad, grad student, or even somebody looking for a postdoc position, well, how do you kind of come to Los Alamos? So student program at LANL is a big pipeline through which we try to recruit people to stay at the lab. Like I had mentioned, I went to the lab as right after my undergraduate as a post-baccalaureate student, where I worked there for about 8 to 9 months. So that's a really popular program where students come and work with us for a year or two. We have about 2,000 summer students who come to LANL for about 3 months every year. So that is another avenue available to students for internships at LANL. If you are a graduate student, we can, a lot of the times, form collaborative relationships with faculty or your advisor, where you might be able to come spend a few months at LANL and do your research there. We have guest programs, and then also we have one of the largest postdoctoral programs for any of the national labs out there. For university and faculty, we actually host conferences and workshops. We have proposal submission processes through certain I think depends on which university you're at, especially for certain universities, to foster those collaborations. We also allow for sabbaticals and extended visits. We have user facilities like the accelerator, where we do neutron diffraction experiments, where people can write proposals to come do an experiment there. And then, of course, we have lots of different joint appointment agreements that we can have with universities, institutional agreements, and we can also write subcontracts to work with people. The reason we do all of this is because we want to attract a world-class workforce at LANL to solve some of the complex problems that we work at. In addition to some of those programs that are more casual and you can reach out to people directly to participate in, we have some formal things, centers in place that we use to collaborate with universities. Some of the centers that I'm involved with, for example, are like Institute for Material Science, so you can do sabbaticals through that institute. We have a Seaborg Institute where we look at actinide science and research. We also have some engineering institutes where we collaborate with a lot of the UCs. But the point of this is that there's many formal and informal avenues for students and faculty to collaborate Los Alamos and visit Los Alamos if that is something of interest. Like I mentioned before, that our student and postdoc program is a huge pipeline for us to recruit people to come work at LANL. I show some numbers from FY20 because that was the COVID year, and that was the time when we had the least amount of students and postdocs come to LANL. We still had about 1,000 student interns and about 500 postdocs at that time that were working there. Most people that become staff at Los Alamos have at some point worked at Los Alamos, either as an undergraduate student or a postdoc or a graduate student. So on the bottom right, I basically show the percentages basically of the total LANL population who are students and postdocs. So this is like a really important recruitment pipeline for us. Just to give you an idea of the type of areas that the postdocs work in, on the right is like a pie chart where you can see that, majority of the postdocs are located in what we call our physics division. I'm in the material science division, and I'm kind of surprised that it only says 32 here because we're a pretty big division, and we have a lot of postdocs. And the point here is that, there's a variety of groups that you can work at in Los Alamos. And one reason people like to work at Los Alamos is there's a lot of cross-divisional collaboration going on. So if you major in material science, but you are interested in working on more engineering-based problems, you can walk down the hall and walk down the road and talk to some engineers in like our W division and come up with a project that would be very cross-cutting areas. The reason I'm saying all this is also because I have a few positions available in my team where we're looking for postdocs with microscopy experience, and we're also looking to hire 2 postbacks, one that can help with some metallography analysis on the type of work I'm going to talk about in a little bit, and then also another with for somebody with a more computational background to help us with some data management. So if you're interested in knowing more about that, I'm going to put my email in the chat box. Just send me an email afterwards and I can send you the job ad, and I will also send that to Krishna and Ankit. So hopefully they can advertise that within their universities. Okay, so what do I do? Let's talk about the technical work. So my day-to-day work is associated with designing materials that can withstand dynamic loading conditions. So what do I mean by that? So if you are in a car crash, you have those crumple zones in the front of your car. we try to design ways of dissipating energy associated with high impacts. So we design materials that can withstand those types of loading conditions. A recent example of that could be a few years ago. I don't know if you remember, but there was that plane in New York that had to land in the Hudson because there was some engine damage because of birds running into there. So we try to design materials that can withstand those type of impacts. It's important for stockpile stewardship. We have a lot of DoD applications, but also for some of the generic applications that I just mentioned. So while I would love to do large-scale experiments where, you know, we crash cars all day long, we can't do that because, one, they're very expensive, and in general, they don't really lend themselves to having us develop an understanding of how materials fail. If we want to design materials to survive extreme conditions, we actually need to understand the mechanisms that drive damage and failure. So what we do is we actually do experiments at the small scale level where we might take some of the materials involved in an application and perform dynamic loading. I'll show you how we do that on these materials to nucleate damage. So if you see, let me see if I can do my pointer. So here's on the bottom of this slide deck are some micrographs where of materials that were impacted to dynamic loading. And you can see in the center of the material, there's a region that opened up. So we try to basically understand how our loading condition leads to the amount of damage that happens in materials. How do we actually do that? And what is dynamic loading? I think that's a big question that people have because this is not something a lot of people learn in school unless you go to school for shock physics. So a lot of you are kind of used to thinking of very simple tests that are done in the lab where material is subjected to uniaxial stress loading, either just compress the material or pull the material to look at how deformation happens and how eventually failure happens. The type of testing that I'm talking about is actually under uniaxial strain conditions. So it's very close to almost like a hydrostatic kind of loading rather than a uniaxial stress loading that a lot of you are used to. The way we do this in a laboratory setting is we take a material of interest, let's say it's this light gray metal, we can impact it with another material. So we basically have a long gun barrel that we accelerate a projectile in. That projectile impacts this material. This material gets compressed. At the time of compression, if you were to plot what's going on in this material, so on the top right, I have a plot that shows the position along the horizontal axis of these materials as a function of time. So your impactor hits your target. That gives rise to a shock wave in your target and a shock wave in your impactor. These shock waves travel to the free surface of both the target and the impactor. And then you get these things called the blue lines here, release waves, that basically are trying to bring your material down to zero stress. When these release waves intersect, it basically creates a region of tension. And depending on how hard this target was impacted, the material two things can happen. One, material can fall apart into two pieces. We kind of term that as full spall. And that's not as interesting to us as material scientists. What we tend to focus on is the other thing that can happen, where you can be very careful about your loading conditions and induce very early stages of damage, where voids are just starting to form in your microstructure, so you can understand where voids nucleate, why do they nucleate in a certain way, because when you're designing materials, you're trying to avoid that. So here is a micrograph of, I think this is copper, showing voids nucleating at different grain boundaries in copper. Okay, we've done a lot of work over the past few years, and I think as material scientists and even mechanical engineers would agree that microstructure of a material tends to control damage and failure in materials. When I'm talking about microstructure, I'm talking about things like grain size, the shape of the grains, the orientation of the grains, and the type of defect densities like dislocation densities, et cetera, that are present in a material. I think there's been a lot of work at ASU with Pedro Peralta, who's also been looking at very similar things. So on the left side, I have some micrographs that I'm showing. This is copper, where we changed the grain size from 30 to 200 microns. The white regions in these micrographs are actually voids that nucleated in this material after it was shock loaded, and then we recovered the samples. And one thing you'll notice is if you go from top to down, that basically the number of voids gets lower and the size of voids gets bigger. So we basically showed in this work that if you change the grain size of material, you start to get larger voids because it's easier for voids to coalesce as they're located along these boundaries. If you add other things like if you alloy basically copper and you repeat similar experiments, here's an example on the right showing that if you added lead versus silver versus niobium, it changed the microstructure that you had and basically changed the total amount of damage in the sample. So we know microstructure controls damage and failure. We want to design materials for extreme conditions. So one easy thing that we can do is control our microstructure. There's many ways that you can modify a microstructure. I think some of the conventional methods involve, like during the casting process, you can control your mold design, you can control your cooling rate. Once you've made a material, you can do post-casting heat treatments to change the grain morphology. There's a lot of work being done in where you can, basically cause severe plastic deformation in your material, using equal channel angular extraction or high pressure torsion to change the microstructure of the material. Or a lot of people use a combination of all of those to modify the microstructure and then understand how that modifies the properties of the material. There are new methods, including additive manufacturing, where people have been using lasers to modify the surface of the material. And also people have been building parts using powder bed additive manufacturing or using wires in electron beam additive manufacturing to kind of generate different microstructures. So on the top right, I show a micrograph of like a conventionally processed material like tantalum. And on the bottom is the same material, but now here we use electron beam additive manufacturing to make this material. And you can see that the grain shape completely changed and the grain size changed. So we're going to use it to our advantage to try to design materials that perhaps do better under dynamic loading. So one way to do this, the only way to do this is to have a process that can be really fast, right? Because one thing we wanted to do is we wanted to sample changes in microstructure in a rapid manner. So we decided to actually use additive manufacturing. And specifically in this work, we looked at selective laser melting techniques. We partnered with the University of Wisconsin-Madison that helped us do the manufacturing piece, and I'll talk about what we did with them, and then we did the actual testing. So I don't think I have to sell additive manufacturing to this audience because Krishna told me that you guys have had multiple talks on additive, but basically, we wanted to use additive because it's fast, it gives us a way of rapidly changing the microstructure. And of course, in the final application shape, we can make complex shapes with this. Here's an example that I got from Madison where they were building little bees that might not be so easy to make using conventional processing techniques. Okay, so we were using selected laser melting. And as I mentioned, during this process, there are many different parameters that can affect your microstructure. There are things like laser power, the speed at which this laser scans, and the hatch spacing between these spacing between the laser passes, basically, that can alter your microstructure. And we wanted to see how, as we change these build parameters, how does that modify our microstructure and then eventually affect our properties. And basically, there's been a lot of work to look at like quasi-static properties of additively manufactured materials, but we were looking at a very specific high strain rate regime behavior of materials, and we wanted to tailor these properties to try to see if we can generate more damage-resistant materials. But we need high throughput manufacturing, and depending on who you work with, additive can be high throughput or not. But we were working with Wisconsin, and they kind of came up with like a really clever technique of making this whole process high throughput in nature. So as I mentioned, we wanted to change power, speed, and hatch spacing during our manufacturing process. And a lot of the universities or like even LANL, when we were doing manufacturing, we would build a lot of samples on a substrate plate, but then it would take us forever to get them off the plate and do characterization. So Wisconsin, specifically Dan Thoma, came up with this approach where they were building samples that looked like hex nuts on a substrate plate. The nice thing about this specific shape was now they don't have to send this plate over for machining. They just use a wrench to kind of twist the samples and get them off the plate. They did about, I think each plate has about 220 samples where they're looking at like 8 different laser powers, 7 scanning speed, and 4 hatch spacing, so various combinations of those parameters. Once the samples are built and taken off the plate, we needed a way of screening these samples because the dynamic tests we do are very expensive and time consuming, and we weren't going to test all 200 samples. So some of the low-hanging properties that we can use to screen for these materials involve things like density and hardness. Density because, you know, a lot of the additives, a lot of the build parameters lead to samples that have a lot of porosity in them, and we didn't want that initially. And then hardness because that can be just a quick screening way of seeing if this material is going to even pass like a baseline strength criteria or not. The cool thing about this process is you can print the materials and do these density and hardness measurements within 2 days, which is pretty fast. Once we have those materials, here's some data. We were looking at 316 stainless steel as a kind of model material that we were studying with Wisconsin. Wisconsin printed more than 200 samples, and then they basically are measuring the density and hardness. And here we plotted as a function of the volumetric energy density that depends on the laser power and the laser speed that I mentioned. The formula is on the top bottom right corner of this slide. As you can see from this plot, most of the samples that were printed had densities that were less than desirable. In fact, here's a region highlighted in the plots where when we looked at the samples, we knew that the samples had open pores. So we decided we do not want to get samples for dynamic testing from this area. We chose some samples from the region where we got maximum density. Similarly, for hardness, you can see that the hardness changes quite drastically with volumetric energy density. And we again chose samples from the region where the samples had the maximum hardness possible. Using these techniques, we actually narrowed down about 9 samples for dynamic testing from about 224 samples. We then take these materials and actually I'm going to skip and I'll go back to that slide. We take these materials and we can perform dynamic testing in our laboratory. So basically on the top right, I'm showing a chamber where this is where my laser pointer is, where we actually put in our target. There's a gas barrel, a gun barrel that you can't see in this picture, but it basically is about 80 millimeters in diameter. We put our targets in there, and a cool thing that we do that's unique in the world, I would say, is we actually recover the samples after they are impacted by a projectile. So they get recovered in this tank, this small tank here that goes into this larger tank. Some of the diagnostics that we use in these experiments are things like photon Doppler velocimetry. Sorry, is there a question? Can people hear me?
Yeah, Saryu, we can hear you. I think there's someone
Okay,
who did.
sorry.
Yeah.
Okay. Anyway, so we use photon Doppler velocimetry as one of the large in situ diagnostics. And what that really is you shine a laser of known frequency on frequency and wavelength on the backside of your sample. As that sample is moving or being accelerated, there's a shift in frequency, which you can relate to velocity, kind of like when you're in traffic and you hear an ambulance as it gets closer to you, the way the siren sound changes. That's basically the diagnostic we use to figure out the velocity as a function of time as the sample is being shock loaded. We also have capability to do high-speed imaging. On the bottom was a GIF that was playing. And this is just one of the gas guns that we have at LANL. We have 2 other gas guns within my team that we use. These facilities let us accelerate samples range starting at 350 meters per second velocity to up to 1100 meters per second. We can basically change this velocity, and depending on the experimental setup, we can estimate what the peak stress is. So we basically say, I want to load the sample at like 2 GPa, and we determine all these experimental parameters. What some of the experimental setup looks like is we take multiple, we want to make sure that most of the samples see the same loading conditions, because the only thing we want to change is the microstructure. To ensure that, we put kind of multiple samples in an assembly. So here at the bottom, the colored regions are the samples. There are 4 samples in this assembly. The PDV probes kind of go in these holes. And in this material, as in this experiment, we were using 316 stainless steel for our samples, for our impactors, and also for these momentum rings around the sample to prevent lateral release waves from coming in. I know it's a lot of detail. If you guys have questions, feel free to interrupt me and ask me now or later. But basically, the experimental design matters, and it is quite complex. But we have world-class facilities that allow us to kind of do these type of experiments that I'm talking about. As material scientists, what we care about is what happens to the samples after they've been shock loaded. So we shock load those samples, recover those samples, we collect the velocity time data, and then we can extract something called the Spall Strength. The way to think about it is that it is stress required to nucleate voids in a sample. Just that's the simplest way to think about it. So we basically looked at 9 samples, and here is a plot where we plot laser power as a function of laser speed, and I color it by Spall Strength. So you can see that out of all the samples that we had, there is a region in the center of this plot where there was a combination of laser power and laser speed that led to the highest Spall Strength that we could measure in these experiments, which was about 3.2 GPa. In addition to these 2 parameters, we had also changed the hatch spacing. So we looked at, here I look at Spall Strength as a function of hatch spacing, and you can see that as the hatch spacing is increased, the Spall Strength goes up a little bit, but mostly if you increase the hatch spacing way too much, the Spall Strength went down. So we knew that we wanted a sample that was built at about 200 watt laser power, moving at 800 millimeters per second, and a hatch spacing of 0.09 millimeter if possible. However, we did not have that sample. We had a sample with a hatch spacing of about 0.11. which had a Spall strength of 3.1 GPa. And we thought, okay, if we can optimize the hatch spacing, we might be able to increase the Spall strength of the material. If we increase the stress required for void nucleation, we've basically made a material better for applications under extreme conditions. So once we determined what we needed, we basically went back to Dan Toma, to basically Wisconsin, and said, hey, can you build us samples that have these combinations of the build parameters? So they built us 2 extra samples. So sample 10 had the hatch spacing we requested. And for fun, they also built us another sample, which was actually the manufacturer's recommendation for the EOS machine that they were using. The maximum Spall strength that we measured in the old series of experiments was about 3.21 GPa. When we repeated the same experiment under the same loading conditions on these new samples, the Spall strength did indeed go up. But instead of like a 25% increase in Spall strength, we got about a 4 to 7% increase in Spall strength. So not a ton, but this was at least able to demonstrate that if we control the microstructure, we should be able to design materials to have very tailored responses under dynamic loading. But one thing as material scientists we're interested in is then trying to understand why that is the case. And when I'm talking about velocity time data, we've done a lot of work that has shown that if you just look at that and you are not able to look at what went on in the sample, you're only getting 1/2 of the story. So one of the things that I mentioned we do is we recover the samples after the experiments. We can cut them open and actually look inside the samples to see what damage looked like in the material. So here are micrographs for some of the samples that were subjected to shock loading. The center black region shows the damage or the void that formed in the sample. And one thing to notice is some of the samples like sample 3 and sample 8, in addition to the Spall plane, have a lot of porosity kind of in the bulk of the samples. So these passed our initial density and hardness screening, but obviously these were not the best built samples. But if you look at the morphology, the shape of the voids in a lot of these samples, as an example, if you look in sample 5, there are very small voids that are kind of separated from each other. But if you look in sample 7, those voids have started coalescing, they're joining together, and you're starting to see larger amounts of damage form. So there, in addition to differences in the stress required for void nucleation, we also noticed a difference in just the evolution of that damage over time. That's also important to us when we're looking at designing materials for specific applications. We don't just like taking pretty pictures, so we actually take those pictures and we quantified the total amount of voids present in the material only in the Spall plane. We normalize when we do our analysis, we make sure to kind of subtract any porosity that was in the material before the shock experiments were done. So here I plot void percentage as a function of Spall strength, and you can see that as the Spall strength goes up, you have lower amounts of voids present in the material, which should be the case. I'd like for you to focus on these 3 points on the bottom right side of the plot. The 2 purple points are sample 10 and sample 11 that we had requested from the university and did indeed have a higher Spall strength and a lower void percentage. One thing that was interesting to us is that sample 11, which was built using the build parameters that were recommended by the manufacturer, actually ended up having the highest Spall strength and the least amount of total damage in the material. If we compare sample 6, 10, and 11, so these are the samples with the highest Spall strength, you can see that the total amount of damage did indeed go down, but we wanted to try to understand why that is. So we did a deep dive where we kind of plotted parameters like grain size, the aspect ratio of those grains, dendritic arm spacing in these samples, and like average grain boundary misorientation that's in the samples. And again, these are plotted as a function of those laser power and laser speed. And one thing we noticed is that the samples in the sweet spot that we're looking in tended to have a large grain size, about a medium aspect ratio. But the thing that stood out to us is they had very low grain boundaries with low average grain boundary misorientation. We've done a lot of work that has previously shown that if you have lower angle boundaries, they tend to resist damage formation as compared to higher angle boundaries. So currently our hypothesis is that these larger grain size coupled with the presence of low angle boundaries is probably helping increase the Spall strength. That is the reason why the new samples we built perhaps are doing better. However, this is something that we're in the process of checking. So in summary, I would say that we have a high throughput approach that we're using to make samples. There was a lot of work that went into making this process high throughput. You know, we didn't want to make 5 samples a week. We wanted to make hundreds of samples a week and rapidly screen them using properties like hardness and density. When we performed dynamic testing on these samples, we were indeed able to increase the Spall strength of the materials by 4 to 7%. We are trying to right now work on some other processing techniques to see if we can increase the Spall strength of these materials even further. And right now our working hypothesis is that, you know, changing the build parameters is altering the grain size and leading to a change in the type of boundaries that are present in the material, which is leading to a higher Spall strength. I have more slides, but perhaps I'll pause here and take questions from people.
Yeah, thanks, Saryu. That might be a good idea. We're already 11:47, so I think we can open it up to the audience, and based on their feedback, I think you can even use the other slides to answer them. But any questions, folks? I think if you have questions, you can put it either on the chat box or just ask Saryu right now. I have a few questions, so I'll wait for others to chime in. Unmute yourself, folks, before you ask the question. So let me start. Saryu, is there, I mean, I know that you do a lot of modeling and you work with a lot of folks, but is there any supplementary or follow-up or supporting evidence from simulations to kind of, I mean, you have the ground truth, so there's nothing to support. But in terms of developing theories for understanding this.
Yeah, so I also do a lot of atomistic modeling, and I didn't talk about that today, but we did do some, we basically built models, polycrystalline or nanocrystalline in this case, models of, you know, just in iron, for example, where we replicated what a conventionally processed microstructure looks like versus what the AM microstructure looks like, those kind of long columnar grains mixed in with those smaller kind of grains that you get. And what we found was that there were 2 things. One, I already mentioned that we are changing the fraction of the type of boundaries that are present in our samples by changing the processing. And then we basically replicated that with atomistic and measured the Spall strength, quote unquote, of how that changes with boundary character. And we found that if you have these special boundaries, the Spall strength was much lower. So the hypotheses that I put in here, we did kind of check that with some modeling work that we've done. And we do that pretty routinely. Yeah. I just didn't have time to also include that in this talk.
Okay, there's a question from Louise.
Yep.
And I'll just read it out for you. Would you please repeat the
I can read it.
Oh, yeah, sorry. Yeah, go ahead.
Oh, no, that's okay. Oh, yeah. Okay. He's just asking if repeat the dendritic arm influence. I got lost that part. So Luis, I mean, to be honest, I kind of glossed over that part too, because one thing we had measured was also the dendritic arm spacing in these samples. And basically, if you look in the plot that's here, we didn't see any specific correlation per se there. So even though we measured that, we don't think that was the reason why we were getting a better Spall strength in the material. So yeah, so we measured it to see if that would influence things, but it didn't seem to have.
Okay.
Krishna, can I ask you a question?
Yeah, of course, Ankit, go ahead.
Yeah. So thanks for a great talk, Saryu. So I have a question regarding the nucleation of voids. So from what I see is the Spall strength is really going to be determined by two factors. That is, if the voids, if and when the voids nucleate, and then the second aspect is if they proceed to coalesce. So those are the two factors, I guess, which will determine the overall Spall strength. So at this stage, do we have a mechanistic understanding of how the voids nucleate in these samples?
I mean, I think we do. We definitely, okay, so I guess there's two answers to that. So we do understand that grain boundaries or other defects in the material, right? We call them weak links. They act as sites where voids tend to nucleate, right? So we understand where and when, for most part, I should say, voids nucleate. Now, the second part of that is, can we model that accurately, for example, in our continuum models, right? And the answer to that part is not quite, because, there's some models out there that try to connect void nucleation with microstructure, but I think they're still in their developmental stages. One thing I would say is the statement that I made that voids are nucleating, at specific regions in the microstructure. So you're pulling a region into tension, and within that volumetric region, there are features like grain boundaries and defects. I would say like 10, 15 years ago, that statement was quite controversial, because the kind of strain rates that you're looking at under this type of loading condition are like 10 to the 5 per second. So people would always say that you're, overdriving the microstructure so much that it probably doesn't even matter. So I would say in the last 10 to 15 years, we have a better understanding of void nucleation. We know if you take the same material and work hard in it, you're basically changing the void nucleation sites in the material, and that will change how many voids nucleate and where they nucleate in the microstructure.
Right. Okay. Yeah. So
does that help?
Yeah, it does. Yeah. So I understand. So when I see these samples, the voids are really aligned along the tensile axis, right? So do you think that more ideas can be derived from these kind of experiments if we were to biaxially and triaxially load the samples?
They can be, but we're looking at a specific loading condition. But you're right. If you change that loading condition, right? If you activate, right, other components of the stress tensor, I think the nucleation process would change for sure. But we haven't looked at that.
Okay. All right. Thank you.
I think we have time for maybe a couple of questions, if at all we have. Anyone?
And if you want to ask me about jobs at LANL, please do. Like I mentioned, we have a few positions that we're trying to fill right now. So if you have any questions about that, feel free to ask.
And Saryu, do you take in undergrads too, or is it mostly only like for summer?
So right now, the two positions that I mentioned are for people with a bachelor's degree. So once you get your bachelor's degree And, let's say people apply to graduate school or want to apply but don't know if they want to go or not, then we have positions where you can come work with us for 2 years and like 1 to 2 years, do research, and it could be less, do research for a few years with us. And then hopefully by then you decide like, hey, R&D is for me and I kind of want to go to grad school, or you decide that's not your thing and you'd like to get a job right away. So yeah, those 2 positions are for post-bacs that I mentioned.
Yeah. Okay. That's good to know, because we always have lots of undergrads, especially in their end of their sophomore and junior years, who also want to go to labs. But I assume these positions are specifically for people in the senior year who are about to be done, right?
Yeah, and I would say for the people who are like in the junior year, summer internships are like the best thing for them to do. So if they come to the lab, maybe let's say summer of their junior year, and they kind of really like it, they can, try to come back after they get their degree also.
Yep.
For
Okay.
the post-bac positions that I mentioned.
Okay. So would this be a good time for the juniors to just touch base with you, not in terms of a position, but to be prepared or be ready next year, same time, if you have these?
Yeah, 100%.
Okay.
I will say that as an example, the deadline for us to hire summer students is March 31st, right?
Oh.
So if you're interested in working with us during the summers, reach out to me like in January or something, so that we kind of figure it out. You can't email us in April to come here in May.
Yeah. No, absolutely. No, that's good advice. I think there are lots of students who really would like to find out more about R&D opportunities and whether they fit in, and this seems like a great starting point for them. Yeah, so we'll definitely keep that in mind when we talk to our undergrads. But even some grad students are always interested in internships, right? So I think we'll ask them to get in touch with you. I mean, for the next year, not for this year, but for 2023.
Yeah, I didn't get in touch with me anyways, right? Even if it's for the fall. So I mentioned the summer program, but really we take students in any time, right?
Yep.
You can come work with us in the fall, the winter, whatever.
Yeah, we will definitely. I think I can't speak for everyone, but there seems to be a huge revival in interest in metallurgy, and everyone wants to get back into metallurgy and additive and those stuff. So it's a big recruiting tool for us to get more students in MSc.
Yeah, I second that.
Yeah, and like I think one thing I will say is, I think what we do in my team is even cooler, right? You get to blow up things, you get to break things and kind of figure out why they're breaking in a specific way.
Yeah.
So
that's always exciting.
Yeah.
Absolutely. So students, any questions? You guys are like being really quiet today.
Yeah, it's been a little quiet. Yeah, normally it's not like that.
Anyone? No, I think they are already plotting to email you, Saryu.
Okay.
So that's great. Thanks you for taking the time off during your vacation. Sorry for imposing this, but this was very insightful and informative from our part. I think it is in our best interest to keep this conversations and partnership going with LANL. As I said, I think we can even think of a Southwest initiative where UFA, ASU, Los Alamos all get together. As I said, there's a big push in metallurgy too, once again. So, and I know it's how important it is to LANL. So,
we would love to do that.
Yeah, cool. Ankit, any parting shots you want to?
No, I mean it's been great listening to this talk, and actually I was not familiar with spalling and those. I mean I have heard about it, but then I didn't have ideas as to how it relates really to the materials that DO is interested in. So yeah, that's a cool talk. Glad to know about these, that these are the current focus areas. Yeah, and it looks like there is a lot of aspects where modeling can also help. That's something I come to know through this talk. Yeah.
Thanks, sir. You have a great